Hi everyone, my name is Argenis Fernandez. I am a principal architect for Pure Storage. Welcome to the PASS Virtual Summit 2020. We're in a session now called Modern High Availability and Disaster Recovery Technologies. As the name says, we're going to be talking about HA and DR topics. We're going to take a little bit of a different spin on HA and DR this time though. Not only are we going to go over the different technologies that exist for providing high availability and disaster recovery, but we're also going to ensure that we focus on the practical aspects of each technology, rather than just going over all the features and knobs that are available for those technologies. I think that's going to be hopefully a valuable use of your time today. And so let's get going. Explore everything PASS has to offer. There are tons of free online resources at pass.org. You can become a PASS Pro member to unlock even further exclusive training and networking for PASS. There's user groups, SQL Saturdays, PASS Marathon, virtual groups, different topics like performance, cloud, high availability, etc. You can also become a volunteer for the community. Yeah, it's a great way of getting involved. So thank you for participating with us. Your feedback is important to us. Please visit the session evaluation link, the left-hand side navigation bar to rate this session. As a speaker, I gotta tell you, there is no better way for me to understand whether I'm doing okay, which parts are working well, which parts are not working so well for the sessions that I deliver to you. And so if you can please submit before this Friday, November 20th at 5 p.m. Eastern, to get a chance to win some prizes. We appreciate it. So as I said before, my name is Argenis Fernandez. I work for Pure Storage, which is a company that sells storage solutions, not just for on-prem, but also for cloud. And so come check us out. We're actually sponsoring this session today. And so a little bit about me. I am a data platform MVP. I've been for 4 years, and now there's a little bit of a gap between the awards because I went to work for Microsoft and the SQL Server engineering team, so the team also known as the Tiger team. I'm also a VMware V expert. I've been for several years, and also a Microsoft Certified Master. If you didn't know about that certification, I don't think I want to spend too much time talking about it. It was a great technical certification Microsoft had, and unfortunately phased out many years ago. So the agenda today is actually fairly straightforward. We're going to go over just a ton of different technologies available for HA and DR. We definitely don't have time to cover all of them in detail. This is only a 60-minute session, and we're going to leave 15 minutes for Q&A at the end. So we're going to focus on, again, the practical aspects of each of all of these things that you see on your screen there. We're going to talk a little bit about your recovery time objective and your recovery point objective, better known as RTO and RPO. Then we're going to talk about backups and restores. We're going to talk about storage snapshots. We're going to talk about log shipping. We're going to talk about replication. We're going to talk about failover cluster instances. We're going to talk about AGs, availability groups. We're going to talk about VM level replication, which is something that we don't discuss enough in the SQL community, in my opinion. And we'll also talk about storage level replication and the implications of having multiple replicas of your data across multiple storage devices. Then we'll talk about the more nouveau technologies out there, like containers, Kubernetes, and big data clusters. And so how do you provide high availability for them? There's going to be tons of information delivered, hopefully. And there's going to be some whiteboarding as well. And so this will hopefully be a good session you guys will like. So getting right into it, do you know your RTO and your RPO? Well, this is sort of like that discussion where you really need to understand as you design and you plan for your HA and DR, and you want to provide the high availability for your systems, and you want to kind of plan for a disaster. How do you understand exactly what your requirements are? And this is one of the hardest parts of the equation, really. Trying to understand exactly what your business requires, absolutely requires. It's not what your business desires, right? There's a fundamental conflict there between what your business would love to have. Your business will love to have a recovery time of a millisecond and a point objective or a recovery point objective time of 0. And so let me explain what those concepts mean. The recovery time objective is how long does it take you to recover or bring back online that system that you're recovering. Okay, and it applies to only a given system. You can have multiple systems in your environment, and each and every single system can have a different RTO. Okay, let's talk about an RTO for a specific system, though. Let's say a SQL Server database. For a SQL Server database to be fully brought back online from a backup, for example, that's going to take a while, right? Because you're restoring the entire database first before it comes online, before the system's available. So the RTO on a backup operation can be potentially large, right? So that's how long it took me to bring the system online. That is the RTO. And then the RPO, which is the recovery point objective, means how much data have I lost since my system went down. Okay, so consider the scenario where you're a bank and you're taking incoming transactions all the time, right? You will want to minimize the amount of transactions that you lose. So hopefully you were getting your RPO as close to 0. But getting an RPO of 0, it's near impossible unless you get multiple systems working together to provide an RPO of 0, because your transactions are not just kept on one system, right? Your transactions are flowing through a series of systems that eventually land in some and a bunch of others. They don't have to live on any one given system, right? But you get the idea. How much data have I lost since I brought the system back online compared to what it was before? That's my RPO. So my recovery point objective is a desire for businesses to be extremely low. Practically, though, implementing an RPO of 0 becomes extremely difficult, like I said before. It involves having multiple systems manage your data and not any one system, because if you do lose your system, what is in flight may be still considered in flight and may be cached or held at a different tier than the system that you're trying to bring online. So let's talk about let's look at this on a whiteboard, and hopefully this will give you guys a better idea of what I'm talking about. So imagine this is your SQL Server database. Okay, this is where you're keeping all your transactions. All right. You are effectively dumping all of your transactions for your bank. You're keeping them in the SQL Server database. If you do lose this database, if it becomes unavailable, and you have to recover that database, how many transactions are you actually going to lose the moment you recover that system, right? If you had to restore the whole database, even if you took a tail of the log backup, there may have been a transaction in flight that may have been issued against your system that hasn't actually hit your database yet. And that is the idea of holding your transactions in some area before it hits the database. So your client doesn't necessarily have to be talking to the database directly. Your client can be talking to something that actually holds your transactions in place. And we can call this just a buffer. But it can be many, many different things. And so the idea is, if you want to provide that super high availability, your transactions may not just live on any one given place. They may be in some different layers within your architecture. And that's what achieving a low RPO actually becomes. It becomes the idea of even handling an in-flight transaction that hasn't quite hit the database yet, in-flight in between your client and your database server, your client application and your database server, so that you effectively have a way to kind of buffer those transactions, so that even if your database server goes down, you have a way of recovering your database server and then flushed all those transactions that were pending against it. So this is a pattern that you will see very commonly on financial institutions, insurance companies, and things like that. So this is really what I wanted to mention when it comes to RTO. Again, the RTO of 0 is difficult to achieve, costly to achieve, doable, but it entails making sure that your entire set of moving pieces in your architecture, your client, everything that's between your client and your databases work together to make sure that the experience of, a piece of data that has been placed in your system does not get lost if any one piece of your system dies. So that entails, that is a rather difficult proposition to achieve. Again, RPO 0, more of a pipe dream. But it's doable though. Most when you talk to your business, they will tell you, yes, we want RPO of 0. But you have to tell them how much it's going to cost them. When they realize how much it's going to cost them, they'll immediately change their mind, more than likely. Unless, you're a very big company and then you know exactly that your business cannot afford to lose any single piece of data. And so determining what is a correct RPO for your business becomes fundamental. Most of our customers are okay with losing 5 minutes of data, but we have those customers that have extremely sensitive applications, like bank, insurance companies, and financials, etc., where losing 5 minutes of data is just disastrous, right? Imagine a bank losing the last 5 minutes of data. That becomes a little bit of a problem, like recreating all those things that happened in the last 5 minutes, even if you have them buffered. Or what happens if you have multiple strikes, like multiple systems go down at the same time, which is common, right? Imagine a ransomware hit. That is also a very common scenario today in the businesses out there. Something disrupts not just one system, but disrupts your entire infrastructure. Recovering from that becomes a little bit of a problem. So let's talk about backups and restores. This is some of the more commonly known technologies out there, right? Backups and restores have been available in SQL Server since the very first version of SQL Server. They were called dumps back there. They were not called backups. Regardless, in the storage industry, we call them streaming backups because the idea is simple, right? You're streaming data from your SQL Server into some backup device. But the problem with backup is that you're actually going through the entire data set. Right now, granted, there's other kinds of backups other than the full, where you only back up portions of your database, like a differential backup, for example, only backs up the changes in your database since the last full backup. But it's important to understand that the full backups in particular are going to be necessary. At some point, you're going to have to take a full backup. And so what happens is there is a size of data operation, meaning you have to go through the entire data set when you're performing that first backup. Right? And so, or that full backup, I should say. That size of data operation, it's not only executed once on the SQL Server that you're reading from, there's also a full-on size of data operation on the backup device that you're backing up to, right? You're reading from one, you're backing up to the other. So let's look at this on the whiteboard. You have your SQL Server here, right here, and let's say that you have a database that it's actually 20 terabytes, right? And you want to take this database and you want to back it up to some some storage that you have down here. So you take that backup, and let's say you're using SQL compression and you're getting a 50% reduction in the data set, which is not uncommon. And you get 10 terabytes written down here. So you see, you went through an entire size of data operation on reading all those 20 terabytes. You spend the CPU to compress that data down to 10 terabytes, which that CPU hit may not be that much, but it can actually be measured. Right. And so we wrote down to your backup device, you backed up 10 terabytes. And now you want to take those 10 terabytes and restore them. Right? You have a scenario where now you have to restore them. Well, now you're doing another size of data operation to read those 10 terabytes worth of data. And then you're going to have to write 20 terabytes worth of data down here. So you see, you did the operation. When you backed up the database, this is one size of data operation. This is another size of data operation. And when you restore, there's another size of data operation and another size of data operation, writing it down to the original storage, or maybe some different instance of SQL Server on a different storage device. Point is, these size of data operations get increasingly expensive the larger your database gets. This is just a fundamental thing to understand. It's not the same backing up a 20 terabyte database as it is backing up a 20 gigabyte database, right? So we're talking orders of magnitude more time because you're dealing with more data. And so fundamentally, backup and restore are great technologies. You want to continue using them, but you also have to be mindful of how long it actually takes you, not only to back up the database and the impact that it takes to back up that database from your production system, but the impact that it causes on your network trying to dump all those backups into your backup infrastructure. that also is measurable and actually costly. And so the other thing that you have to account for, and even more important, is, that's great, you have a backup. Have you tested it? Testing it means restoring it and then running consistency checks on it, for example, to get a degree of confidence that that backup is a valid backup, that you would actually be able to restore it whenever you do need to restore it. So the question becomes, the most important question is it going to restore? Yes. Also, how long did it take to restore? Because if you have a 20 terabyte database and you do have to restore it, you're reading 10 terabytes worth of data from your backup device, writing it down to your storage for your database. All of that is going to take a long time, and so your RTO is going to be heavily impacted by the fact that you are going through all of these types of data operations. So this is a fundamental aspect of backups and restores that you have to consider for HA and for DR. So let's take a few minutes to talk about storage snapshots now. We consider the case of backups and restores, right? Full-on size of data operations for the backup itself and for the restore itself. So what if you didn't have to do that? What if you had a technology in your storage device to back up your database and without a size of data operation at all, right? Something that's instantaneous or almost instantaneous and gets you a good copy of your database that you can recover from. Now, storage snapshots are a little bit of a religious discussion, really. If you ask me if I would trust a storage snapshot 15 years ago, I will tell you you're absolutely nuts. I'm not going to trust that technology. Or maybe I'll use that as a plan B for my recovery of my database if my streaming backup didn't work, rather than make that my plan A for recovery. But today, that technology has been revamped significantly, and storage snapshots are much, much, much better today, especially if you're using them with newer storage technologies like all-flash arrays or hyperconverged storage infrastructures. Anyway, the idea behind the storage snapshot is you have your volumes that comprise your database. They're actually volumes in your storage device, or maybe virtual disks on your storage on your HCI infrastructure. Can you take images of those volumes, right, at a given point in time, and then restore your database from that? And so there are two kinds of snapshots. Traditionally, this has been the way they've been described. There's the app consistent snapshots, the application consistent snapshots, and those are the snapshots that SQL Server knows about. Okay, those are the snapshots that utilize the VSS framework within Windows and the SQL Writer service within SQL Server. And so the way that they actually execute is there is a VSS requester, which could be some backup software, for example, NetBackup or Commvault, okay, or maybe Rubrik or Cohesity, or one of those. Or it could be just a plugin provided by your storage vendor. For example, we at Pure Storage provide the SSMS extension that is a way for you to take VSS-based snapshots, app consistent snapshots. Anyway, the VSS requester places a request to the VSS stack within Windows, saying, hey, I want to back up this particular database. And the VSS framework wakes up and says, oh, you want to back up this database. Is anyone here listening for requests for databases to be backed up? The SQL Writer service says, yeah, I know how to handle that. I just need to tell you all of these volumes are involved in this particular database. I'm going to go ahead and flush my IO buffers. I'm going to cause a checkpoint to be taken on the system. And then at that time, I'm going to quiesce all the IO that's being issued against my volumes that comprise my database. So there's a complete freeze of IO. Actually, the quiescing of IO is done through an undocumented call called dbcc freeze IO. When that happens, there is a callback to the VSS hardware provider, which is a piece of the VSS infrastructure that's connected to your actual storage device, that issues the actual call for a snapshot against the storage device. So once everything is nice and quiet, you can go ahead and take the snapshot at the storage level. And so once that snapshot is completed, that typically doesn't take very long, you can return, and then those volumes that were quiesced, remember the IO was frozen in those, can then continue, and then processing can continue in your database. So that has a few implications, right? Implication number one is if you had very tight SLAs on your queries, at the moment you take a VSS-based snapshot, you could potentially disrupt those SLAs because you have to go through all of these calls, all these operations need to take place, and then finally you can take a snapshot on the storage side. That, again, can be costly. You will feel the pinch. And as a matter of fact, you will see entries on your error log potentially saying that there were IOs that took 15 seconds or longer, depending on how good or how bad your infrastructure is for storage. And so they're great, right? The moment you take those snapshots, those snapshots are ready to be used as restores. But I wouldn't call them backups just yet, okay? The only way that I would call those backups is if you start offloading those snapshots from your storage device, however that is, into something else that is completely separate from your current infrastructure. Okay, so for example, if you're using a storage array, you want to start mirroring that snapshot. The moment it finishes completing, you start mirroring it off somewhere else or copying it off somewhere else, potentially even the cloud, right? Somewhere where you know you're going to have a good copy of that data. Otherwise, that is not a backup. Okay, it only becomes a backup when you have another copy of it somewhere else, not on the same device where your database resides. And that's actually fundamental. Going back to the kinds of snapshots that exist out there, I mentioned the app consistent snapshots, right? Those are, again, the ones that SQL Server knows about. And they actually provide, this is very important, the application consistent snapshots provide point-in-time recovery. So you can roll forward transaction logs on top of a backup restored with no recovery. So you take a snapshot taken with VSS, there's a restore operation available for it where you can choose just to say, I want to restore this database with no recovery, so that you can then roll forward transaction logs on top of it and perform what we call a point-in-time recovery operation. So that's important to understand. The other kind of snapshot that's available on the storage side is just called crash consistent snapshot. And the reason why it's called crash consistent is because it's taking exclusively on the storage side. Windows doesn't know anything about it, or Windows or Linux, depending on which flavor of SQL Server you're running, or even if you're running on containers, Linux doesn't know anything about it. SQL Server doesn't know anything about it either, right? Yet it still can contain a good copy for database. Now, not every storage vendor actually calls their crash consistent snapshots 100% reliable. So be careful with that. What I mean to say about the reliability of those snapshots is that you should also test them. Just like you test your regular backups, you restore them somewhere else, you should take your snapshots, restore them, attach them to some other SQL Server instance, and run your consistency checks on them. Okay, so going back to the crash consistent snapshots, they are great, though. Although you don't have point-in-time recovery, you can take them frequently on your storage devices and then replicate them off to some other storage device, maybe potentially the cloud, and get those copies of your databases going as fast as possible. There is little to no impact, depending on the underlying architecture of your storage device, for those snapshots being taken. If you would have asked me, do I see any performance ramifications from a snapshot taken on a storage device 10 years ago, I will tell you yes, there are plenty. Mainly because storage arrays will run on top of disks. Storage arrays these days run on top of flash, so things are handled very differently, right? There's no copy on write kind of thing happening when you are just pushing data into the original volume for your database. It has to be copied into the snapshot volume because they're different, right? These days, storage arrays work very differently. So, and even hyperconverged infrastructures take snapshots and they handle those snapshots very, very differently. So it's fundamentally important to understand that the crash consistent snapshots can be good, meaning if your storage vendor tells you that they're safe to use, you can rely on those snapshots to recover your database from them. As long as every single transaction log write makes it into that device and it's included into your snapshot, along with your data files and everything is, those snapshots are taken consistently and atomically across all the volumes involved, those are going to be called good snapshots, right? So be mindful of several things here. Whether you can take crash consistent snapshots taken on the storage side of things, rely on them or not, talk to your storage vendor about that, and also whether you do need to use application consistent snapshots. If you do take application consistent snapshots, complementing your streaming backup infrastructure or your native backups that you take for SQL Server, then you want to make sure that your snapshots that you take on the storage side are taken with copy only. So your app consistent snapshots are taken with copy only. So that way you don't disrupt the LSN chain for your differential backups that you take on your regular native backups. So let's talk about log shipping. Log shipping is another technology that's been around SQL Server forever, and it's one of the best ways of getting data from one SQL Server instance to another. Right, so the main SQL Server instance is called the primary and log shipping, the second, and then you have the log shipping secondaries as well. So the idea is not only do you take one full backup of your database and ship it over to your secondary, but you take those transaction log backups that you take on your primary instance and apply them to the secondary. And there are a bunch of considerations with log shipping. The biggest consideration, in my opinion, is whether you're going to use standby or not on the secondaries. Standby means, can I read? Do I have to issue read-only queries against those databases? The answer is you can, as long as you're not log shipping to a newer version of SQL Server, right? Because the moment you upgrade the database on the target side, you can no longer receive incoming transaction log from the previous version of SQL Server, which, by the way, that's one way of migrating things from one SQL Server to the other. You just log ship to that newer version of SQL Server, and that's how you kind of migrate. But the important part is, every time you do standby, if you have to run queries against the database for whatever reason, crash recovery has to be run against the database every time you apply, every time you say standby. And so that is important, because that time that crash recovery takes to bring the database online can add up to the overall effort for log shipping of bringing the database to a new reporting time. However, it's also important to understand that log shipping can have a time delay, right? You can say, I don't want to apply any transaction logs that are newer than the last hour. And that gives you a mechanism for you to go back to in case something happens to your primary, in the case of data loss, for example. So if I issue a query, for example, that has a delete that has no where clause on a given table, and you end up deleting all the data on it, you can potentially go to that log shipping secondary and grab data from that table as it was as of the last time that you applied a transaction log backup to that secondary, and bring that data into your primary. Same goes for an object lost, for example. If you drop the store procedure and somehow you can't find it in your source control, you're using source control, right? You would go to that log shipping secondary and fetch that object, script it out of that secondary, and bring it into your primary. So multiple scenarios you can do, like tables, for example. I dropped a table. How do I recover it? You can go to your secondary and fetch it from there. But again, the consideration is for log shipping is not only do you have to have two copies of the data, right on the primary and one on the secondary, potentially many more secondaries. You can have as many secondaries as you wish. Really, I don't think SQL Server actually has an advertised limit to how many log shipping secondaries you can have. Maybe they do, but I don't remember right now. Point is, it is a good way of scaling out your copies of your database, because you're just shipping log to all of them. And that can be a good way of dealing with things. Your log shipping secondaries, you can sort of fail over between your primary log shipping database and your regular shipping and your secondary. The way that you would do that is by taking one last transaction log backup with no recovery, so that your source database becomes unavailable. That last transaction log backup is copied to the secondary, and then you bring that database fully online on the target side, and you've effectively sort of migrated that database from one server to the other. All right, so let's talk about replication. Replication also has been around SQL Server forever, really, many decades, I would say, at this point. And so the fundamental, I'm just going to talk about transactional replication, because that's the mainly replication topology in use out there. There's also merge replication, P2P replication, blah, blah, blah. not going to talk about those right now. I'm just going to focus on transactional replication, which can be used for providing high availability in SQL Server, right? Imagine you have your primary SQL Server that you're issuing transactions against, and what you're doing is taking those transactions and just replicating them down to another SQL Server. In the event of the failure of the primary SQL Server, you just go ahead and fail over to that other SQL Server, repoint your applications to that other SQL Server that you were replicating to. Now, some of the considerations of replication center around initializing subscribers, which are the downstream servers in the topology replication, right? So you have your publisher and your subscriber in replication, or many subscribers, right? So the idea is initializing a subscriber entails a full-on size of data operation for the objects involved in replication. So if you have very large tables that you have to initialize in your subscribers, there's going to be a full-on size of data operation, BCPing that data out of your publisher, and then BCPing in that data into the subscriber. So that's effectively how it works behind the scenes. There is a way of using or leveraging backups and restores for initializing the subscriber. That's called Initialize Formalism. Right, so you basically restore a database, and you tell the publisher, hey, you have this new subscriber that's going to start from this particular transaction log backup, right? Or maybe even maybe even in a given backup file. The idea is once you start, you can kick off replication right after, because the replication subsystem knows which LSN to continue replicating from for that particular subscriber that you just added, right? The distribution system understands LSNs versus commands issued. It keeps all that information on that database. So effectively, there is no mechanism for only sending portions of the data for initialization. Okay. It's an all or nothing proposition, and that becomes a little bit of a problem if the data sets that we're talking about are extremely large. If you have to initialize a 20 terabyte database, right? So it's 20 terabytes worth of data. You may not even have to reinitialize the whole database, or maybe that portion of the database is large enough that it's measurable in several terabytes. A backup and restore operation can be very lengthy and can actually cause some issues, in terms of how long or the availability of your systems while you do that operation. There's a nifty trick that we came up with at Pure Storage, and it essentially entails using a SAN snapshot, a storage-based snapshot, for initializing your subscriber using the Initialize Formalism method for replication. So the idea is you take a storage snapshot of your primary database, then you attach it to your secondary database, and then you query the transaction log for the last LSN that's been committed for any of the tables involved in that particular subscriber, also in that particular publication set. So you have the sets of articles that are actually replicated. You will figure out which one was the last LSN that's committed, and then you will tell SQL Server to kick off replication from that. And that's kind of a nifty trick, because you are, again, avoiding the full-on size of data operation caused by the BCP or the backup, and then getting your replication kickstart from a storage snapshot like that. All right, so let's talk about failover cluster instances. This is technology that's been around forever as well, and a lot of you are still using it out there, and for a good reason, right? It's solid. It just works. There are some quirks with it, like all these timeouts on the cluster and things like that can become a little bit of a pain. But by now, most of you are probably very comfortable with managing this technology. The idea behind failover cluster instances is that you have at least two nodes, and these nodes are looking at a common storage, so a shared storage that is can be seen by multiple nodes, and those nodes can be physical bare metal nodes or can be VM nodes. And so, there are some considerations for what kind of storage can you use when you're using VMs for failover cluster instances, whether you should be using failover cluster instances on VMs to begin with, because some folks consider the technologies that come with the VMs to be good enough that you don't really need to have a failover cluster instance set up on top of a hypervisor. Look, that becomes a little bit of a religious discussion, to be honest with you. I think that it's perfectly fine to set up failover cluster instances on top of hypervisors whether you're talking VMware, or whether you're talking Hyper-V, or whether you're talking Nutanix, or any of the other hypervisors out there. It just works. This stuff it has been tested, has been widely deployed, and it's enterprise ready, more than enterprise ready. So, problem with a failover cluster instance, though, is that you have that common shared storage, and that kind of limits things in a way, right? What if something happens to that storage? So typically, you're mixing a failover cluster instance topology with some other topology that offers data replication, like an availability group even, right? A failover cluster instance can be one of the replicas in an AG. It's just that it's not very common to see. Some folks use it. I used it in the past. But not only can you use, FCIs with AGs, but you can use FCIs alongside other kinds of data replication. So what people do, and big enterprises do, we see this a lot in Europe, for example, customers are replicating their shared storage underneath the hood for their FCIs, and stretching their failover cluster instances across different data centers. And this concept of stretching a cluster has also been around for decades. I don't even know how long it's around has been around for, but it's been around for a long time. The idea is that if you swing the node, so there's your node is actually looking at your storage on data center A, because you're replicating it underneath the hood. You would just have to fail over your compute where your SQL Server instances run, and then they would see the same storage on the other side, and that's kind of the idea behind stretching a failover cluster instance. So you're relying on a single copy of the data, though you don't have the same all that goodness that comes from an availability group. Though it's a very different model, because you have a shared storage model, and an availability group you do not have any of that. But the fundamental thing is, if something happens to that storage, you're going to have to rely on some other protection mechanisms for that storage to recover from them. So they're typically sitting on top of some enterprise storage device that provides some sort of capability for recovering in the event of a failure. So you also have to consider what happens if I have to upgrade my storage, right? High availability on the storage side is very much a thing. Understanding what is the impact of doing an upgrade on my underlying storage can be a fundamental decision as to how you're going to implement your topology for HA. Right? If your storage device takes too long between patches, then you may not want to rely on something like a failover cluster instance, because if you're all looking at the same copy of the storage, and that storage device it's going to take too long for it to be updated, then your database is going to be down during that period. And if that's unacceptable, then there you go, right? Then you have no option but to do something other than failover cluster instances, or maybe an availability group that you can swing your primary replica to one that is not leveraging the same storage device that is being upgraded at that time. And so those are important considerations to understand, right? Also important to understand, newer storage devices don't suffer from very lengthy periods of downtime when they're being upgraded, right? Where you needed to make sure that all the VMs are offline, there are no SQL servers running at the time, right? That used to be the case 15 years ago. This is no longer the case these days. You can just patch your storage devices at the same time that your SQL Server databases are running on top, as long as there are newer, proven technologies that allow you to keep your databases online while those devices are being patched. So again, talk to your storage vendor. It's very important that you understand what's available underneath the hood. If you don't manage your storage devices yourself, then go talk to your storage admin. You should having a good or your VM administrator, right? These folks should understand what's available in your environment. All right, here we go with the controversial one: availability groups, just AGs for me. AGs are fantastic, right? You get your primary replicas, and you get your secondary replicas, and then you can even have distributed AGs where you have a completely different set of primaries and secondaries that may live on a completely different domain, blah, 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 blah. They are great. I'm not going to go into the innards of AGs and how they work, etc., etc. But I want you guys to understand what happens when you use availability groups, right? Not only do you have multiple copies of your data, which is a good thing, right? You want multiple copies of your data in case something happens. You get that wonderful page recovery technology, right? So page level restores that happen automatically. If a page goes bad on one of the replicas, it goes and asks the primary replica, you send me a copy of it, and the primary will gladly provide a copy of that page so that it can be applied to that secondary and bring it in and continue on with the processing. That is a fantastic feature, right? And just like that, you have other features of AG that are great, like the listener, right? The listener can direct your read-only queries to the battery of read-only replicas that you may have, et cetera, et cetera. But the problem with availability groups is seeding of the availability groups. In general, this becomes a little bit of a problem when your databases are extremely large. There's also considerations around performance, modifications, heavy modifications against the database and how they're handled, et cetera, et cetera. This is a topic that takes a really long time to discuss in depth. But I really want to highlight how hard it can be to actually seed an availability group, a set of availability group replicas that are in the multi-terabyte range. Imagine that you have a 20 terabyte database again. If you had to seed that availability group replica, not only do you have to have a copy of your primary, but you have to have a copy of the database in every single replica. And if you are using asynchronous replication and you're replicating to some other data center, so you have a replica sitting on another data center, a geo-distance data center, you have to send a copy of that database. It doesn't matter if you're actually using automatic seeding or whether you're using the traditional backup and restore model for restoring that database. You're going to have to go through that entire, or through several sites of data operations to get that data set across to that target data center, and then restore it so that you can then join the availability group. So more issues central availability groups are around the performance aspect of it. There are some pretty significant limitations on the amount of data that an AG can actually handle at any given time. Meaning, if you're making a lot of modifications in a sustained way to your database, AGs may not be the preferred method for high availability for you. That's just because SQL Server can handle pretty well the ingest of data, but replaying those modifications or redoing those modifications into the other replicas can become a bottleneck pretty quickly. And so if you have a significant amount of data that does have to be modified, or big ETL jobs that entail sustained modifications to the database and the hundreds of megabytes per second or even gigabytes per second, you are going to run into potentially some pretty nasty situations there in terms of perf. So you have to be very careful on how you design your architecture systems so that they have plenty of CPU, plenty of memory, and even more importantly, a great networking subsystem and a great storage subsystem so that you can serve all of those IOs at very low latency and provide the oomph that those systems need to replicate all that data and then reapply those log buffers to all the other replicas involved in the set. Now, seeding AG replicas, again, the two traditional mechanisms are auto-seeding and backup and restore. There's also a way to seed availability groups using storage snapshots, and that's another technique that we have been also talking a lot about at Pure Storage. And so the idea is that you take a snapshot of your primary database and then you apply that snapshot to your replicas and then seed your availability group that way. That's also a consideration that becomes a little bit important when you start mixing storage snapshots with underlying replication technologies at the storage level, right? It doesn't have to be a traditional storage array like ours. It can be hyperconverged infrastructure from the likes of vSAN or Azure Stack HCI, etc. As long as you can get those snapshots replicated across to the other side where you do need to seed that availability group replica, you may do this trick, right? So the idea being, take a snapshot, restore it on the replicas. If it's an application consistent snapshot taken on the primary, you can restore it on the replicas with no recovery, so then you can join the availability group that way. Or there's this other trick that we have been demoing for our customers, and it works extremely well. The idea, and incurs into downtime, so it's a little bit nasty in that sense, but it works. So the idea is that you can just take all your availability group, your entire availability group down, right? Previously seeded your databases with an empty database, just a shell database with the right files and the right file IDs, kind of like Hackattach works. If you guys are not familiar with Hackattach, you may want to look at that. And so log shipping Hackattach is what you want to search for. So the idea is that you have a shell database with all the files and the file IDs matching your actual database. Have that auto-seed, that empty database, have that auto-seed across all the different replicas. Bring down your SQL Server instances. Just overwrite with storage snapshots all the volumes where those files are supposed to be with the actual data from your database, and then bring everything back up. Just bring your entire availability group online. This is a little bit of a non-orthodox way of seeding availability groups with crash consistent snapshots. You can do this as well. And so if you're interested in hearing more about this, contact me during the Q&A that we will have at the end of this session. All right, let's talk about VM replication. This is something that we don't talk about enough, right? Your VMs that actually run your guest operating systems, right, your Windows operating system or your Linux operating system, can be replicated, okay? You can segregate those areas of the operating system that are ephemeral, like your swap partitions or your swap files, put them into separate volumes that are not replicated, are not part of the replica set, and just have those replicated over to other hypervisor infrastructures on a different data center, maybe, or maybe on the same data center, depending on what your topology is like. But the idea is that you're replicating the compute portion of things. Okay, you're just replicating the VM per se. There are ways of replicating the entire thing, right? VMs and databases all together at once, but they typically cause a lot of trouble because if you back up the VM at the same time that you back up your database, you can cause this problem called VM stun, where the VM takes way longer to be backed up because you have to also engage the VSS for your databases as well. And so talk to your backup vendor about this. If you're using the likes of Commvault or Veeam or Rubrik, etc., for any of these things, or Cohesity, you want to make sure that you discuss with them what is the best way of backing up your VMs. But backing up SQL Server instances this way is a valid method, and you may be using it in your enterprise today, just so you don't know it. Right? I personally like the model where I replicate my VM, but I don't replicate my database along with the VM on the same side. I don't treat them like the same unit. I kind of decouple my VMs and my storage from my databases, so I can treat the two independently. If something happens to my VM, I still have a copy of my database that I can go to. Right, I have treated that separately, and I don't have to worry about any interdependencies between them. And so the question typically becomes, what about your use system databases, et cetera, et cetera? Look, when you're replicating the whole VM, you don't really have to worry about system databases, right? But when you're replicating just your user databases, then you do have to worry about system databases. So the question becomes, what parts of the system databases do you care about? Do you care about the users? Do you care about the jobs? Do you care about any objects laid out in the database that may not be fit within those two? Those things you have to consider. You have to replicate somehow. So you have to make copies of them somehow. You have to synchronize between replicas or different SQL Server databases somehow, or instances somehow. There is Dba Tools that may help here. So Dba Tools, if you haven't heard about them, they do. It's a community-driven project that does a set of PowerShell commandlets that can help you with a ton of different tasks, including replicating things across multiple databases. So replicating objects across databases, etc. So this is something that you may want to peruse. But the idea here, then the one thing that I wanted to highlight is the fact that VM replication is a very valid way of replicating your database, providing high availability for your databases for your SQL Server instance. There are hypervisor-specific pieces of functionality for doing this, right? So VMware has their own replication technology. Microsoft with Hyper-V has their own replication technology, et cetera, et cetera. The idea is having this VMs replicated either to another hypervisor cluster, et cetera, can provide you high availability for your SQL servers that way. And so Sometimes it makes a lot of sense to do things that way because it's a good method, widely used out there. Storage level replication. I've kind of been talking about this throughout the presentation, but I wanted to make sure that we touch upon it and make it perfectly clear of the different options that exist out there. I'm going to focus a little bit on what Pure Storage does because that's where I work, but the rest of the storage vendors out there have very similar technologies to what we offer out there. Some are easier to use than others. The gist of it is there's three ways of replicating your storage that we offer today. There is a synchronous replication, right, where you have two storage devices and whatever writes you issue against one device gets automatically replicated to the other storage device, and you don't acknowledge until it's actually hardened on the secondary device before you mark it as completed. That one write that you issued against storage device A doesn't get replicated, does get replicated to array B, and then not only until it gets hardened on array B is when it actually gets acknowledged on array A. So it works very much like availability groups in sync mode, right? So let's look at it on the whiteboard. You have your storage device A, and you have your storage device B. You have your SQL Server host or VM running on top, and you are issuing writes against storage device A, right? Whatever write you issue against A is copied to B. It is hardened on B, acknowledged as completed from B to A, and then finally acknowledged to the host operating system or the guest operating system as completed. Very much in the same way that availability groups work in sync mode, right? Where every single thing that you issued has to be acknowledged on the secondary replica that's in sync mode before the primary replica can acknowledge as completed. So we call this technology active cluster. Our competitors have different names for the way that they work. So it's essentially synchronous replication at the storage level. This has the peculiarity that you're going to introduce latency, some latency, potentially very little. If your storage devices sit within the same data center, you have excellent networking between the two. You can make sure that latency caused by the fact that you have to synchronize IOs across two storage devices, it can be minimized and it can be measured in microseconds, right? So you can actually keep your IO very, very fast. You don't have to use this particular method of replicating IO synchronously at the storage level, though. You can also replicate asynchronously, right? And in that scenario, we're doing the same thing as we're doing here, right? It's just that the one thing that we're not doing is waiting for that acknowledgement, right? So SQL Server writes down to storage device A, and the IOs are kind of packed together and then shipped from A to B without waiting for acknowledgement on A. So processing can continue on A all the time, and you're just sending asynchronously those IOs to the target storage device. And so we call this, at Pure Storage, we call it active sync. A lot of other vendors have, again, different names for it, but the idea is the same: asynchronous replication of data in a sort of journaled fashion from one storage device to the other. And so talk to your storage vendor, see if that kind of functionality is available to you. But you may be wondering, well, is there another way of doing things? You mentioned synchronous and asynchronous. Is there another way? And the answer is yes, there is another way. So let me show you how that works. The idea is you can take storage snapshots on your storage device A, and those storage snapshots can be replicated to storage device B. So you have kind of point-in-time images of those volumes replicated from array A to array B, or storage device A to storage device B. I call them array because that's always sorry. So you would have that library of available points in time at the storage level, not at the database level, that you can recover from. And so that's another way of replicating things from one storage device to another. You take an image of a set of volumes, you package them together in a unit of work, you replicate that unit of work downstream to that storage device. And then potentially you may fan out into multiple storage devices that you're replicating to. The storage device, again, doesn't have to be in the same data center. It can be, sitting across the globe in a completely different country. The point is, this is a very effective way of safeguarding your data as well. If your snapshots, again, can be both app consistent or crash consistent, depending on your storage vendor. So talk to your storage vendor for more details. But that's sort of like the overview of how you can do replication at the storage level. But we didn't talk failover, did we? So we want to sort of make sure that we understand what we're talking about here. And so what I'm going to do is just show you the idea behind, synchronous replication, asynchronous replication, or storage-based, storage snapshot-based replication. How will you do a failover of things? So in the case of a synchronous replication, you have SQL Server writing to instance A, to storage device A. Those IOs are being replicated to array B, acknowledge back to array A, or storage device A, and then acknowledge back to SQL Server as completed. So if you lose this infrastructure, let's assume that these reside in two different cages, right? Your data center. So this is DC1 or DC region 1. So data center region 2. You have here low latency between the two. So let's say you have 5 milliseconds of latency between the two. If you're also replicating your SQL Server VM to this data center along your databases, you could end up with a scenario where if you do have a failure where you lose all of this, you can just swing your VMs and swing your storage, and now these links have been servered, but this SQL Server instance can actually start from that, that VM can actually see the data that it needs to restart operations from there. So that's kind of how Failover will work. And we'll work in a similar way to when you're using asynchronous replication. And in the same way, in the case of a snapshot being replicated, there's very different storage vendors handle it different ways, but you can just take that snapshot and clone it into a volume that you can then attach to SQL Server and then continue processing from them. So that's kind of the overview of how storage replication works with HA. All right, so we're in the home stretch now, and we're going to be discussing a little bit about the technologies that are available for containers, Kubernetes, and big data clusters. So as you guys well know, big data clusters are powered by Kubernetes. So backing up a big data cluster essentially means backing up the Kubernetes cluster and then backing up the HDFS portion of the big data cluster, right? So where all that HDFS goodness sits, right? That may not be governed by the same Kubernetes cluster, right? So the Kubernetes cluster may not understand much about it. So specifically for a BDC, you're going to have to back up the Kubernetes cluster typically independently from the HDFS data. So you're going to have to figure out what technology you're going to use for Kubernetes and what technology you're going to use for HDFS. They're typically going to be very different depending on your infrastructure and your needs. For Kubernetes specifically, there's a few vendors out there that provide solutions for backup, HA, and DR for Kubernetes, right? Some of the most renowned out there are Velero, Kasten, and also Portworx, which was now acquired by my employer, so full disclosure there. These vendors provide different sets of technology for backing up, providing high availability, and providing disaster recovery capabilities for your Kubernetes clusters. But when you're talking about backing up your HDFS data, you're going to have to figure out how do you deal with that particular portion of it. So it becomes a discussion with your storage vendors. If you have your traditional HDFS cluster that's split across, different independent nodes, you're going to have to back up the data independently, and so forth and so on. There are some tools available for that that allow you to kind of dump all the HDFS data. But what most folks do when it comes to HDFS is just replicate it, right? They do some sort of storage-based replication for an existing HDFS data set into something else, right? It can actually be cloud or syncing objects between on-prem and cloud, or cloud and on-prem, or even between clouds, or a multi-cloud kind of scenario. Becomes very much a thing for protecting that HDFS data in your big data cluster. And specifically for containers, just standalone containers. We don't see a lot of adoption of just standalone containers without an orchestration layer for SQL Server in the enterprise. Now, that has all the reason in the world to be, and that's because you typically need an orchestrator for figuring out what to do if a container needs to be restarted, right? If a container dies for whatever reason, or if a container is not responding, and what if the Docker host when you're running that container or some whatever container runtime you're using, what if it dies? How can you respawn that container somewhere else? The answers to those questions are typically lie on finding a good orchestrator for that. And Kubernetes seems to be the de facto container orchestrator of choice for the entire world, it seems. And so the conversation here becomes, how do you decide to back up your Kubernetes cluster? How do you decide to provide high availability for your Kubernetes cluster? Can you take the entire set of containers and take a point-in-time image of all of those containers at the same time? Whether you're talking master instance of SQL Server, you're talking data pools, compute pools, can you back up all of that up at the same time? And can you also kick off, how to have a point-in-time image of your HDFS data sets at the same time that you backed up all of that data in your big data cluster, so you can have consistency across HDFS and the rest of the big data cluster. Things become a little bit more difficult when you start considering the fact that big data clusters are not made up of just a big data cluster per se, but you could have all these different satellite systems that are providing data virtualization, that you're providing data virtualization for, right? Remember, big data clusters can actually reach out to Oracle instances, SAP instances, or MySQL instances, or what have you, and then virtualize those data sets as external tables within the big data cluster itself. So how do you provide an entire backup of everything becomes a little bit of a difficult discussion, right? So you need to understand if there are any data dependencies from when you do take a backup on any given part of the system or any of the satellite systems, and how does that affect the overall performance of the big data clusters. Let me give you a spoiler there. The least dependencies, the data dependencies that you have across the systems, the happier you will be, and the easier your implementation of big data clusters will be in your enterprise. Well, with that, thank you so much for attending my session today. I hope it was beneficial. There is definitely plenty of time left still for Q&A, so I'm going to be, obviously this is a recording, but I am going to be live and ready to answer any questions that come in the Q&A. Thank you for coming today.